Hello everyone. Today I am hereby to give a presentation on deflection due to bending. Now I will give a small introduction myself. My name is G. Sanat Reddy. I am a title of the presentation is deflection due to bending and I bearing a pin number of 21955A 2109 and that's it. Next, abstract. In this presentation we were able to derive the equation of deflection due to bending, and we will discuss some term which is related to the deflection due to bending, that are neutral axis, direct stress distribution formula, and unsymmetrical bending, and what is meant by symmetrical bending. Let's get into the topic. Introduction. Before starting presentation, we should come across some basic concepts which makes deflection due to beam easy to understand. Next, first, neutral layer. The layer that exists between upper and bottom surface and which does not change its length when it undergoes the bending is called the neutral layer. Next, neutral axis. The line of intersection of neutral axis on the plane of cross section of a beam is called neutral axis. And next, bending stress. Normal stress induced in the beam due to action of bending moment is called bending stress. Next, moment of resistance. The moment of resistance of a beam is the moment of the internal force about the neutral axis. For equilibrium, the moment of resistance must be equal to the applied bending moment. Next, radius of curvature. Radius of curvature is defined as the distance between the center of curvature to neutral layer is called radius of curvature. Now let us discuss about what is meant by symmetrical bending. Symmetrical bending of a beam, also known as uniaxial bending, occurs when the load plane coincides with some of the main axis of the beam cross section. It is a figure of symmetrical bending in which we can able to understand that the beam is said to be a symmetrical beam. The beam is said to be a symmetrical beam if the selected beam is uniaxial, in which if we fold the beam along any axis, then we can able to it will perfectly coincidence with the axes. If we observe in this figure, we can able to understand. If we consider a rectangle, it is said to be an symmetrical beam. If we consider the I section, it is said to be an symmetrical. And if we consider the C section, it is said to be an symmetrical about x axis only. If we consider the T section, it is said to be a symmetrical bending about y axis, not all x axis. Next, let us discuss about unsymmetrical bending. In unsymmetrical bending of a beam, also known as complex or biaxial bending, the main axis of the cross section do not coincide with the direction of loading. By this figure, we can able to understand that the L section is not said to be the perfect symmetrical, so it is considered as unsymmetrical bending. And if we will consider the Z section beam, and it is said to be unsymmetrical beam, which means it is not symmetrical about any x axis or y axis. Therefore, it is said to be the unsymmetrical bending. Next, now let us get into a topic: deflection due to bending. As you know that a beam bends about its neutral axis. Now suppose that at some section of unsymmetrical bending, the deflection normal to the neutral axis as shown in the figure below. Next, and for the position of the center of curvature and for the usual approximate expression for curvature, we have 1 by psi is equal to d square. Then we will get the below equation. Next, the components of u and v are in the negative direction of the axis x and y respectively, so that we can able to achieve the above dimensions. The above equation, u is equal to minus of psi of sin alpha and v is equal to minus of psi of cos theta. From this figure we can able to derive the deflection due to bending. If you observe the x-axis and y-axis, the neutral axis is the position at which it will change. In the second case, after the deflection, after the change in the distance of the beam, we can able to understand that the center is came to the origin. I think next, differentiating the above equation twice with respect to z and then substituting for z in the first equation, then we get the below the equation which is provided in the equation. And next, then we will obtain the below equation. After substituting the all value, then we can able to get the achieve this, the formula which is projected in the presentation. And next, from the directional distribution, which means by the directional distribution, we can able to get the formula, that is 1 by rho into sine of alpha, which in which we can able to, and when we will come across this formula, we can able to understand that it is belongs to a directional distribution. Therefore, that from the directional distribution we can able to get the above equation. And next, substituting the sine alpha by p and cos alpha by p in the expression given below, then we will get the above formula. In which the above formula, in which it describes u double differential, and as you know that u is an x component and v is an y component. As you know that if the u 1 dash means integration of component along x-axis, differentiation of component along x-axis, which gives a displacement, and after deriving the equation we will achieve, after deriving the equation we will get the deflection, as the u double dash intimates the deflection of the x component, and the v double dash will describe the deflection of the component belongs to the y direction. Next, by rearranging the above formula, then we get my by my mx by my is equal to minus e of ixy in ixy ixx by iy by ixy u double dash and v double dash, in which we will return the direct stress distribution formula in terms of a matrix. Then we can able to achieve the above formula. And next, by solving the above equation, by just solving the above equation, we can able to achieve the further steps, that is mx is equal to minus ei xy u double dash minus ei about xx section into v double dash, and my is equal to minus e iy u double dash minus ei xy v double dash. The above equation can be written as, and which means we can able to rearrange the equation. Then further, in which the cx or cy as an axis symmetrical, in which the moment of inertia about the xy coordinates is 0. Therefore, by substituting the ixy 0, then we can able to reduce the above equation, that is u double dash is equal to minus moment about y axis by eiy. Next, then we will get v double dash is equal to I mx by EIXX. Conclusion. Therefore, by this presentation, we have derived the deflection due to bending, and that is u double dash is equal to, means deflection about the x component is equal to minus movement about y axis by E into moment of inertia about y axis, and then V double dash is equals to minus mx by ei into ix. By this we have completed our presentation.